Thank you, Mr. or Mrs. Moderator, whoever you are. You're just smiling. I see you, Riley. So, my project is Triclosan and Plankton. Oh my! Because they make a really weird combination, let me tell you. But before I get started, I would like to thank a lot of people. First, I'd like to thank Mr. Dutton, Mr. Diesla, Dr. Lund for providing me with the intelligence I needed to do this study. My parents for putting up with me while I was doing this study with things like aerators and billions of mason jars and so much things. Riley Brown, Brianne Blyden, Madison Perkins for helping me record and collect my data and also record this video that you're watching, Mr. Dutton. The audience for being here today and listening to me speak. I know that you didn't have to be here, but thank you anyway. And my fellow Governor's School students for providing me with emotional support when I really needed it. So some key points before we get started. Over 206 million pounds of chemical waste is dumped into US waterways per year. They can be found in everyday items like toothpaste, antibacterial soaps. I mean, who here washed their hands today? Hopefully you did after you used the restroom or whatever you were doing this morning. Chemicals have been known to cause an increase in diseases for humans and also cause hormonal damage. And that can be rather bad. I don't know what I was going to put there, but yeah. So my backstory, I've always wanted to be a doctor. Like, it has always been my dream, and I wanted my senior research project to have something to do with it. It didn't have to be directly related, but had to be around there. I was showering, like, you know, typical person, everyday routine, and I turned over a bottle of soap. It wasn't even my, like, body soap. It was, like, hand soap over on the side of my sink, and it had this weird chemical on it called Triclosan. I thought to myself, well, what is Triclosan? And so I looked it up. Triclosan is C12H7Cl3O2. I almost messed that up, but yeah. It was patented in the 1960s and distributed in multiple items, and it has a 60 to 100% detection rate in US waterways. It works by blocking an enzyme that pretty much helps bacteria and plankton create an outer shell to protect themselves from things like, I don't know, chemicals. And it has been shown to affect human hormones. So that's how I kind of thought up, well, yeah, plankton. Plankton are affected by this, just like bacteria, right? And if plankton gets sick, humans get sick. So hey, medical, like, that's medically related. And eventually I came to, what are the effects of Triclosan on plankton in the Elizabeth, Rappahannock, and Potomac River? I just said that completely out of order, ignore me. And pretty much I figured that my study would be helping the world, because if plankton are getting infected, then humans will get affected. And eventually it'll just cause world chaos, right? Mr. Dutton, you're going to have so much to say tomorrow or Thursday or whenever I talk with you. So my independent variables were Triclosan at 0, 0.2, 0.4, 0.6, and 0.8 grams. I know, a mouthful. But they were all diluted into 100 milliliters of water. And the three rivers, the Potomac, the Rappahannock, and the Elizabeth River, I totally got that in order this time. And my dependent variable, because I didn't change the slide, Mr. Dutton, were my alkyl densities again. So the three locations that I picked had to do with their proximity to my house and also to my heart. So first it started with the Potomac River. As you can see, I picked sites that had some sort of human impact. This is right by the Potomac River Bridge, and it has multiple drainage areas, multiple beaches, cars going over the bridge every single day. The Rappahannock River, which is in Tappahannock, I actually took my data from St. Mary's, which is right here. And again, that's like a lot of human impact along where I took my data from, which was very important. I forgot a major point. The reason why my hypotheses will be the way that they are is because of the grades that the Potomac, Elizabeth, and Rappahannock River had in 2011 and the ones that they have now. So the Potomac River went from a D ranking, which means that it was barely alive, but it was still alive and it was still thriving, but it could have been better. And now it is currently at a C. And the Rappahannock River used to be a D+, and it is also now currently at a C. And the Elizabeth River, which I used to live in Portsmouth, Virginia, so I was right by the Elizabeth River. And while I was there, it was failing, it was dying, it was not okay. It was going to, people were saying that the river was going to die, and that nothing would ever be able to grow around the area again. And I'm proud to say that it is currently at a C ranking, and that can mostly be said thanks to the Elizabeth River Project. And Bay Avenue, which goes along one of the many bridges in Portsmouth and around that area, Norfolk, is Bay Avenue, and pretty much, I'm really sorry I just got redundant there, Mr. Dutton, but I took my data from Bay Avenue. And so due to the fact of their past ratings, I decided that the Elizabeth River would have the most algal density, since I assumed that plankton had become resistant to certain chemicals, much like bacteria can become resistant to chemicals. And therefore I assumed the Elizabeth would have the most algal density, the Potomac would have the second most, and the Rappahannock would have the least. And then for triclosan, I assumed that as triclosan concentrations increased, algal density would decrease. So the way that I did my study, I went out to each river and I towed plankton for 5 minutes, collecting 100 milliliters of river water with plankton inside of it. I waited for it to settle for an hour, and I added 100 milliliters of mineral water. Please excuse me if I sneeze. After the water had settled, I took a 10 milliliter sample and I put it on a petri dish with 100 centimeter squares, and I counted each plankton individually underneath the microscope and times it by 20 to match the milliliters that I had created. Then I added the triclosan concentrations that had been diluted into 100 milliliters of water. I waited for it to settle again for an hour, and then I recounted. I also had a constant which didn't have anything added to it, so I could calculate percent change, and I took another 10 milliliter sample after adding the triclosan, and I counted it again, and this time I multiplied it by 30 to reach the milliliters that I had created. So pretty much what I found was that the rivers were rather similar at each level of concentration. I'm not taking the concentrations here. What's actually being taken is the average amount of percent change found in each river. So I'm not doing the effect of triclosan on rivers, I'm doing the effects of the rivers on percent change of algal density. As you can see here, the red is the Potomac River, the Rappahannock River is blue, and the green is the Elizabeth River. And again, just this negative trend as triclosan concentrations increase, or as each river changed with the concentration, percent change decrease. So like it got lower and lower, it went from 0% to negative 100%, which means that it was decreasing. However, for the rivers, I had a p-value of 1.89 times 10 to the negative first, which means that the rivers did not have an effect on algal density. However, that does not mean they are unimportant. It means that they were more similar than I first thought. So pretty much a negative trend overall, and again, the error bars show that they were just too similar. There were errors somewhere in my study. I'm not sure where, but I'm sure I'm about to get into that somewhere. So as you can see, then I took the triclosan concentrations and I did that versus the percent change of algal density in each river. I just screwed up back here. Okay, so I rejected my null hypotheses, Mr. Dutton. That's what happened. And as you can see, on the y-axis, there's percent change of algal density, and on the x-axis are the rivers. I'm really sorry. You're going to murder me on Thursday. Anyway, so triclosan concentrations versus percent change of algal density in each river. First, there was the Potomac River, which you can see is in red. On the y-axis, I had percent change, or the average percent change of algal density in each river. And on the x-axis, I had triclosan concentration grams per 100 milliliter. So again, just this negative trend as triclosan increases, algal density increases. And as you can see, the Rappahannock River has this area at 0.2 grams of triclosan per 100 milliliter, where it's higher than the Potomac River or even the Elizabeth River. So that must mean that there was something wrong at 0.2. Perhaps I misdid my calculations. There are multiple possibilities, but overall, the trend is still negative, and the error bars aren't as big as first assumed. Mr. Dutton, we need to, what? Mr. Dutton, we have to talk about that. Why is that doing that? Because shouldn't the error bar be bigger? Okay, well, whatever. And then at the Elizabeth River, again, a negative trend, but overall it had the most linear reaction to the triclosan. It followed into a line and the error bars were rather small. So again, and I also need you to resend me that email, Mr. Dutton, because the p-values, like, I'm getting confused. Anyway, so yeah, trend lines, negative and bad. This pretty much proves that there is a negative trend in algal density due to triclosan concentrations, and therefore I reject my null hypothesis and accept my, why am I saying accept my? I'm not supposed to say that, I don't think. Anyway, I rejected my null hypothesis, and therefore triclosan concentrations do have an effect on algal density. And that means that each river is similar, and it also means that if we improve river health, then we're also improving chemical waste problems on plankton and bacteria and other organisms that we rely on. My bad. For our everyday life, because plankton and phytoplankton and bacteria, they provide some of the most concentrations that we need in certain aspects. O2, things that we breathe, things that we make a lot of our items out of rely on bacteria and phytoplankton and plankton. So yeah. And then, just in case, Mr. Dutton, there's going to be a picture of the jars and light in there. I'll get that tomorrow probably, and you're going to yell at me. But anyway, I'm really sorry. This is probably about 15 minutes long. Don't kill me. Bye.